Today we are going to talk about structure and function of liver. Primarily this lecture is about the histology of liver, but this is very important to understand because in so many liver diseases this histology alters. That is what we call it, liver histopathology, and you are supposed to know as doctors liver histopathology very well when you talk about the liver diseases. So first we will talk about the liver histology. Liver is the largest internal organ. In adult person it is approximately, how much is the weight of it? Yes, in adult person, who can tell me approximately weight? Try to guess. It is about 1.5 kilograms, right? You can say the weight of liver in an adult person is about 1,500 grams. Of course, that becomes approximately 1.5 kilograms, right? This is the largest internal organ, right? And another way to express its weight is that it is usually 2.5% of your total body weight, 2.5% of total body weight. Now liver is situated anatomically, right? Anatomically it is situated in a very strategic situation that all the blood which is coming from the GIT and pancreas and from the spleen, right, it is passing through the liver, right? This has a lot of implications. For example, all the nutrients which you are absorbing from the GIT, first they will go to the liver and then they will go to general circulation. Then if unfortunately if you have absorbed some toxins from GIT, first they should pass through liver and get detoxified in the liver so that general circulation is not exposed to those toxins, right? In the same way from the spleen, one of the function of spleen is to destroy the old RBCs, and remnants of those RBCs which are being destroyed, they may come to liver, and liver has also RBC clearance mechanisms, Kupffer cells, so that they should be removed. Then of course blood from the pancreas is also going to the liver, so that from pancreas insulin and glucagon and other important hormones should go to the liver, so that under the directions of those hormones liver can handle the glucose and handle other nutrients and metabolites, right? So first of all you should understand that liver is very strategically present between the GIT, spleen and pancreas on one side of the liver and general circulation on the other side of the liver. Liver is in between. Is that right? Let me put a very simple diagram that let's suppose, first of all I will explain a little bit about circulatory architecture of the liver, that how the liver cells are getting the blood, right, and how hepatocytes or liver cells are exposed to the blood. The first thing which I told you, that here is your GIT, right, and here is your spleen, here is your pancreas. So what I was telling, that blood from all these organs is going to the liver, right? Blood from the GIT, of course this is the venous blood from the GIT, as well as splenic vein, right, as well as from pancreatic venous drainage, all of this is going to the liver. This is first thing you should understand, right? Again, from GIT lot of nutrients, they must go to the liver so that liver can handle it. For example, if you have eaten a food with lot of carbohydrates, so extra amount of glucose which is going to the liver should be converted into glycogen, so that a level of glucose in the general circulation should not go very high. Suppose here is your general circulation, and eventually of course from the liver blood will drain into general circulation, right? This is one thing from the GIT. Secondly, from GIT toxins can be absorbed, bacteria or their toxins can be absorbed, or inadvertently you may have ingested some toxins. So many of these toxins should pass through the liver and liver should detoxify them. Is that right? Another way, it also acting as a detoxifier so that it protects the general circulation from the toxins which are coming from GIT, right? Then from pancreas, blood is also going to the draining to the liver, so that pancreas adding to the blood to insulin, glucagon and other hormones, and those hormones will act on the liver cells so that liver cell can appropriately handle the nutrients and metabolites which are coming from the GIT. Then I told you that blood from the spleen, splenic vein, that is also eventually draining its blood to the liver, so that in the spleen when RBC's breakdown is going on, the remnants of those breakdown should be cleared off by the liver so that general circulation should not receive those remnants of RBC destruction. So in this way, liver is draining the blood which is coming from GIT and from the pancreas and from the spleen. All this blood which is coming to the liver, this is coming through which vein? Yes, Gary. Mr. Gary is going to impress all of us. Yeah, portal vein, excellent. So this is your portal vein. This is your portal vein. But there is one problem, that blood which is coming through the portal vein, right, this is venous blood, right, because from the aorta, blood has gone to these organs. It has gone to GIT, right, it has gone through to the splenic artery, pancreatic arterial supply. So actually from the aorta, oxygenated blood went to these organs, and these organs have utilized some degree of oxygen from the blood, right, and then when this blood from these organs recollect and going to the liver, is that right, it is having lesser amount of oxygen. Again, let me explain. What was happening? That blood which was going to the spleen or to the pancreas or to this part of GIT, we call it splanchnic circulation. In splanchnic circulation, when arterial blood come to these organs, right, oxygen has, significant amount of oxygen has been utilized. So blood which is going to the liver through portal system, this blood is not very rich in oxygen, even though it may be rich in nutrients, it may be rich in metabolites, or unfortunately it may be rich in toxins, or it may be rich in many hormones, but it is not very rich in what? Oxygen. To manage that problem, nature provide direct supply. There is a celiac artery here, and one of the branch of the celiac artery directly supplies the liver with the oxygenated blood. So it means that liver is getting double blood supply. There is double blood supply going to the liver, right? This is your portal vein, and what is that? What is that? Hepatic artery. What is that? Hepatic artery. Hepatic artery. Let me draw it more clearly. We'll put the liver in proper perspective with the whole body circulation. I will draw this diagram more clearly. And okay, here I draw the right heart. I'm going to draw the whole circulation just to put the liver into proper perspective, circulation of the liver. What is this? Inferior vena cava, that is superior vena cava. Here we have the right heart, right atrium, right ventricle, pulmonary artery. Here you have your left atrium and left ventricle. From here we can say what is coming? Aorta, is that right? And this is your systemic circulation. Now what I'm going to do, that I'm going to put the liver into proper circulation. Of course, all of you must be knowing, here is the lungs, and pulmonary blood is going to the lungs, and there it breaks down into pulmonary capillaries. It gets oxygenated, and oxygenated blood comes to the, yes, left. Is that right? Now, where the liver is present, liver is present in our diagram, we'll put it here. I'll make it a little downward. And liver is here, right? Here is your spleen. It is not an anatomical diagram, it's a functional diagram. Here is your small intestine, am I right? Let's suppose here I put your pancreas, right? Now, the arteries, there are arteries which are bringing blood to these organs. For example, to the spleen, blood is coming from, yes, splenic artery. Is that right? Then there are mesenteric arteries, superior mesenteric arteries, gastric arteries, and there are arteries which are taking blood to stomach. Okay, I'll make it from here. Blood is coming to stomach and then it is coming to, yes, small intestine, and also from here it is going to, what is this? Pancreas. Is that right? Now, the point which you have to understand, that blood which is coming to GIT, right? Of course, this blood which is coming to GIT, arterial blood, it is well oxygenated, right? This blood is, these arterial vessels are eventually breaking down into capillaries. So there are splenic capillary system here, splenic capillary system here. Of course, pancreas also has capillaries, isn't it? And of course, within the GIT also there are capillaries. Is that right? Now, from these splenic capillaries or pancreatic capillaries, or from these gastrointestinal capillaries, blood will be recollected. Blood will be recollected into venous channels. Is that right? Now, from these capillaries, blood is recollected. Now, when blood is recollected, it is going to be drained into portal veins, right? Now, here is superior mesenteric vein and splenic vein will also fuse with it, right? And superior mesenteric vein is this one going up. And what is this? Splenic vein coming from here. So, splenic vein and superior mesenteric vein, they fuse together and they make, what is this? Yes, please. Portal vein. Is that right? Now, what we have understood, that the blood which is coming from splenic vein and this is superior mesenteric veins, this blood is originating from capillary beds of pancreas and spleen and the gastrointestinal system. So this blood which is coming here, it has lost some of its oxygen to GIT and spleen and pancreas. So it is relatively poor in oxygen as compared to arterial blood. This is your portal, yes, vein. So nature wanted to supply well oxygenated blood to liver as well. For that purpose, from aorta there is a celiac trunk. Have you heard of it? Okay, that's good. One of the branch of celiac trunk is, yes, hepatic artery. This is your hepatic artery. And hepatic arteries also bringing the blood to the, yes, liver. This is hepatic artery. Right, so we can say there are two inputs to the liver. Now, blood should pass through the liver. For this purpose, I will explain a little bit the internal architecture of the liver. The parenchyma of the liver is mainly made of hepatocytes. Hepatocytes are the special cells which are making the parenchymal cells of the liver, right? The functional cells of the liver. Now, hepatocytes within the liver are arranged in special lobular structures, right? Those lobules are explained in many ways. One of the way to explain them is classical explanation, we call it classic lobules. Now I will draw here classic lobules. This is, I will go into detail of the whole lobule. We will study it in big detail, but right now I'm just going to draw some of the classic lobules present in the liver, in which hepatocytes are arranged in a very, very special fashion. Right? Now I've made these three classic lobules. Now what really happens here? Actually, from the hepatic artery, as hepatic artery enters into liver, it breaks down into smaller branches, hepatic arterioles. And arterioles will go to every corner of, what is this? Classic lobule. At every corner of classic lobule, this is almost hexagonal arrangement. Now you look, these arterial branches, they are coming at every corner. So it means that every classical lobule, now I will not use the word classic lobule, I will just call it liver lobule or hepatic lobule. At every hepatic lobule, at its corners, we have one branch of hepatic artery, right? And this branch is bringing fully oxygenated blood. Is that right? But in this structure, not only we need oxygen coming from this area, but we should bring all the nutrients and metabolites to this area to be treated by the hepatocytes. So, portal blood should also come over there. Actually, portal vein also breaks down into many, many small branches. And you will be surprised, at every corner, what is this? A branch of portal vein will be present at every corner. So, at every corner of every lobule, a branch of portal vein is also present. Now what we really see, that in a classic lobule, at every corner of it, hepatic artery has given its supply as well as portal vein has given its supply. Is that right? Then what will happen? Okay. Actually, a special type of, in the center of it, I'll make with a different color. In the center of this lobule, there is a vein here. This is called central vein. What is it called? Central vein. Now look at it. So beautifully designed. From these corners, there are capillaries, because these are wide bore capillaries, we call them sinusoids. Sinusoids are extending from the corner to the center in every lobule. Are you understanding it? What are these? Sinusoids. Is that right? And what is really happening? The blood from portal vein, look at it, the blood from the portal vein and blood from the hepatic artery, both of them drain into sinusoid. Let me make one lobule outside, right? I will draw one hepatic classic lobule here. I'm taking this ring and this structure and enlarging here. And let's see what's going on there. Now, at every corner, what we are having? Yes, please. Branch of a portal vein, and with that we are having one arterial branch from the, yes please, hepatic artery. And you know how they have come over there, isn't it? Is that right? Now, What is present here? Central vein. Central vein. Now what you have to understand that from here, these are the sinusoids which were going to the periphery to the central vein. Is that right? These are the, yes please, sinusoids. Now what is really happening there? Actually blood from hepatic artery is coming into this sinusoid. It is feeding that. And from the portal vein also, blood is coming into that. So what is happening? Sinusoid, every sinusoid is supplied by portal blood as well as hepatic arterial blood. Is that right? So our hepatic arterial blood is coming to every sinusoid as well as, yes, portal blood is also coming to every sinusoids. Here I think it's worth mentioning that about 70 to 80% of blood coming to liver is from the portal vein, and 20 to 30% of the blood coming to liver is from the hepatic artery. So hepatic artery is bringing less blood but more oxygenated. Portal vein is bringing more blood but less oxygenated. Is that right? But eventually the blood which is coming from both sides will mix in the hepatic sinusoids. Now blood will keep on moving from the periphery to the center. Now I will show that blood is moving from the periphery to the center. So we call it, it is centripetal blood flow in the sinusoids. And this is a mixed blood from portal vein as well as from, yes please, hepatic artery. Now this is a very unique and special type of architectural arrangement. Why it is so? Actually, here are your hepatocytes. Hepatocytes are arranged in plates. This is a plate of hepatocyte. There is also a plate of hepatocytes here. Right? In the same way, now, through what really happens, sinusoids are very, very leaky. You know, they're very, very leaky. I will explain their detailed structure later. So, whatever blood is coming, the plasma of it comes to this area, right? And it is coming, and from here it is exposed, all the plasma which is passing through sinusoid, it is well exposed to hepatocytes, so that hepatocytes can work on that plasma. If toxins are coming, they will take up the toxins and detoxify. If extra glucose is there, they will take up the glucose and make glycogen, right? Or if hepatocytes have to produce plasma proteins, they will synthesize plasma protein and secrete to this. Now this special space is called space of Deci. What is the name of the space? Space of Deci, right? So what really happens, again, I will make two plates of hepatocytes here. Now, what we really see there, okay, I will make it with different colors, space of Deci. This is the area which should be called space of Deci. Here is also space of Deci. It's a very important area. You know why? Because this is also called subendothelial or subsinusoidal area. This is the space of Deci, which is just outside the sinusoids, and whatever plasma is moving through the sinusoids, it is in free exchange with the space of Deci, and one face of the hepatocyte is to the space of Deci. Through that, right, through this space, hepatocytes can make exchanges, right? They can take up the substances, whatever they absorb, and whatever they want to secrete, they can secrete there. For example, everyone knows that hepatocytes synthesize albumin. So they will synthesize albumin and secrete it into space of Deci, and from there albumin will go into sinusoids. Is that right? So this acts as an exchange area between the blood flow which is passing through sinusoids from the periphery of lobule to the center of the lobule, right? Meanwhile, you know, hepatocytes also secrete bile. In between these cells, here the bile is being secreted. This is the space in which bile is being secreted from hepatocytes. Are you understanding it? Right? So what we can say that hepatocyte has one phase to treat the blood, other phase which is to the bile system. Now look at it. Bile is secreted by these cells and it is moving in which direction? That is moving, yeah, outward. Bile is moving in this way. Is that right? So again, if we talk about this, here also these cells will be secreting the bile, and bile will be moving from the center to the periphery. So this is centrifugal flow of the bile. This is centrifugal flow of the bile, but blood is centripetal. In the same way, look, in the space of Deci, whatever, in the space of Deci, the fluid which is coming, plasma fluid which is coming, it is having some exchanges with the, what is this? Hepatocytes. Then that plasma is going back. Are you understanding me? Or I'm teaching myself? You understand it? That's good. You're not sleepy. Right? So what is happening? Actually, as blood is entering here, not only blood is moving forward, but a part of the plasma is coming out and then it's going back, or coming out and then going back. Is that right? But some of it may not drain back. Some of it may not drain back. That amount which is not drained back, that will convert into lymph. That will convert into lymph. And lymph will flow outward. And here also lymph will flow outward. So it's worth understanding that blood is moving towards the center. Is that right? And this is portal blood and hepatic arterial blood mixed through the sinusoid, moving from periphery to center. As it is moving, plasma freely exchanges with the fluid in the space of Deci. Plasma moves to the space of Deci and then it is taken back. Some of it fluid which is not taken back will move outward in the lobule as lymph. And in between the hepatocytes, right, they are secreting the bile, and that is also moving outward. So let's deal now with this side. Now you will tell me what is happening to this side. It's your test, what you have learned. I make, here are the hepatocytes. What are these? Plates, right? Fine. First you will tell me, what is this blood moving? Through which channel? Sinusoid. It is connected on the periphery to the branch of portal vein and hepatic artery. And centrally it is connected with the hepatic central vein. Blood is moving through the hepatic sinusoids from the periphery to the center. This is clear? Then it has many, it's highly porous capillaries. Is that right? I will go into detail of this later. I'm just telling you how the fluids move through that. Now, what is happening? That plasma will come out from here. Is that right? And to which space plasma is coming? Space of Deci. And then after having some exchanges with the hepatocytes, plasma coming out into space of, yes, Deci. Then it will go back. Is that right? No problem in understanding this? Meanwhile, hepatocyte has this phase. This phase of the hepatocyte is dealing with the blood, right? Toxins are coming through that. They will take up the toxins and detoxify. If too much glucose is coming, they will take up the glucose and convert into glycogen. If insulin or glucagon are coming, they will alter their function according to their signals, right? Or if they want to synthesize, if they are synthesizing the albumins, they will secrete to space of Deci and then albumin will go to the blood. or they are synthesizing coagulation proteins, coagulation factors. They will secrete into space of disc and then it will go, right? But some extra amount of plasma or plasma fluid, most of it enters into space of disc and then goes back. But some which remains extra, which is not drained back into sinusoids, that will drain to the periphery and that will convert into lymph, right? So lymph is moving from the center to the periphery. Now, in between the hepatocytes are draining on this side, they are secreting on this side. What is the substance? Bile. And bile is moving from the center to the, yes, periphery, right? So movement of the blood is from periphery to the center. This is called centripetal flow. And movement of the lymph is from the center to the outward, and movement of the bile is also from center to the outward, and this is called centrifugal flow. Is that right? Now look, as there are input systems, there should be drainage system also. So drainage system on this side should be, yes, what should be here? What is this? Lymphatic channels. And what should be here? What is this? Bile will be, yes, I have not made the cells here, bile will be coming there. Is that right? Now we can make simply that this is the lymphatic, which is a drainage system, right? And here we can make, what is this? Bile duct. So how many things are present? How many channels or systems are present at the corner of this classical lobule? There are 4 systems. But unfortunately, because early histologists did not recognize the lymphatics, so they thought there are only 3 systems. There is a branch of portal, there is a branch of portal vein, there is a branch from portal artery, and they thought there is, what is this? Bile duct. Okay, I'll make bile duct black so you really don't get confused. Right, this is exactly, it should show its cells so that you do not get confused in the diagram. I'll make bile duct with this color but in a double way. Right, this is bile duct. So originally doctors thought that every corner these 3 things are present and they call it portal triad. What do they call it? Portal triad. So, but later on, of course, they knew it is not portal triad, it is portal tetrad. Is that right? Or simply we call it portal area. What do we call it? Portal area. So, at the outer corners of the hexagonal lobules, we have portal areas. In every portal area, we have portal vein input, we have hepatic arterial input, and we have 2 drainage systems. There is lymphatic drainage system and bile duct drainage system. Is there any question here? No. Now we come back to this diagram. If we look at this diagram, so how you will mention that blood is moving from the periphery to the center. Is that right? Any problem in understanding this? Right, so blood is moving from the periphery to the center into these hepatic classic lobules. And of course, you should not forget to mention that what is this moving from the center to the periphery? Yes, bile. Is that right? And in the same direction, what is moving? Lymphatic, lymph. Is that right? No problem up to this. Now, central veins, these 3 central veins, they will come together. Yeah, now they are draining. Yes. These central veins will take the blood from the center and they will drain into sublobular veins, right? What is this vein called? Sublobular vein, and the sublobular veins will come together and make, what is this vein? Who will tell me the name of this vein? Yes, hepatic vein. And hepatic veins will eventually drain into where? Into, yes, inferior vena cava, right? So in this way, you can look at in circulatory system how the liver is really working. Is that right? That blood is, again, there are two input system, hepatic arterial input and what was this? Portal venous input, right? They are making, both of them are making their branches at the corner of classical lobule. From the corners, blood from both systems drain into hepatic sinusoids, which is moving from the periphery to the center. Then it collect into central vein. Central vein come out and they drain into sublobular vein and eventually into hepatic vein and to the inferior vena cava, coming back to the right heart. Is that clear? No problem into this? Another thing. At the same time, we can see this bile system is draining in the periphery. So at every corner, what is this? Bile duct. Is that right? And these bile ducts will also come together like this. Are you understanding me? Right? These bile ducts from every corner, and this is left hepatic duct, and what is this? Right hepatic duct. And they will come common hepatic duct, and of course some of you must be knowing there is something called gallbladder. Is that right? And what is this? Cystic duct. This duct from the gallbladder is, this one is cystic duct. So again, let me explain. This is right hepatic duct, this is left hepatic duct, making common hepatic duct meeting with cystic duct, and now converting into what? Common bile duct. And what is this going down? Is common bile duct. I will draw the whole structure here, so once forever it must be clear, hopefully. It's a side diagram, but it is a very important anatomical implication. And what is this here? Yes? What is this structure? Pancreas. Great. Now what really happens? This is right hepatic duct. What is this? Left hepatic duct. And what is here? Common hepatic duct. And from here, which is coming here? I will make the gallbladder here so that from the gallbladder, what is coming here? What is this? Cystic duct. And now all this together is called common bile duct. It is coming behind the duodenum, of course, coming to pancreas. And what is this duct? Pancreatic duct. And then common bile duct and pancreatic duct come together and they open here into duodenum at the ample of Vater. Here pancreatic juices and bile will come down. Is that right? Again, the relationship is right and left hepatic duct into, what is this? Common hepatic duct meeting with the cystic duct, making, what is this? Common bile duct meeting with the pancreatic duct, and both of them, common bile duct bringing the bile and pancreatic duct bringing pancreatic secretions, they come together and open at ample of Vater into second part of duodenum, so that they release in the duodenum bile and the pancreatic juices. Is that clear? Let's have a break here. Now we will go in detail of the liver lobular structure. The liver parenchyma and its arrangement of the hepatocytes can be explained in three ways. We should explain it in reference to classic lobule, which I mentioned previously. Number 2, we will explain it in reference to portal lobule. Another way to look at the liver architecture, and still one more way to look at the architectural and functional aspect of the liver is when you talk about hepatic asanas. Right, I will first draw the classic lobule, right, 3 or 4 of them, then I will explain other 2 types as well. When we talk about the classic lobule, okay, I think I need to make it a little bit smaller. It has gone beyond my board. How many lobules are there in your liver? Many. Many mean how many? Yes? Too many, okay. I think you are millionaire as far as these lobules are concerned. Alright? You have millions of these hepatic lobules. These structures which I am drawing, these are basically classic lobules. Right, now you will tell me the structures. This is a branch from hepatic artery, yes, and one branch should be present at every corner of this hexagonal structure, which is classic lobule, and this is right hepatic artery. And what is this branch at every corner? Portal vein. Is it right? From the portal vein. And here we have bile drainage, right? So bile duct. Yeah. I've changed the color scheme a little bit, and this is now your bile duct. Right, and of course you remember there were lymphatics also here. These are lymphatics. Oh, I don't know, this lobule is underserved. What's wrong with it? We should put here portal, and yes please, what else we need to put? Bile duct. So this is portal triad, but actually there is always lymphatics also in this area. Now you will tell me what is this in the center? Central vein. Right? And now we will come back to our arrangement. What was from here? Yes, sinusoids, right? I will just draw 2 sinusoids. Now, exactly how is the structure of sinusoids? Sinusoids are made of endothelial cells, but these endothelial cells are not making a continuous lining. They are discontinuous. And these endothelial cells are having fenestrations. These endothelial cells are having fenestrations. So these are, sinusoids are wide diameter capillaries which are extending from the outer part of the classic lobule to the inner central vein, and they are lined by endothelial cells, but endothelial cells are not completely lining us. There are very, very big gaps, and even within the endothelial cells there are very large fenestrations, and these fenestrations are diaphragmed. Plus, there, what is this? Basal lamina Even basal lamina is discontinuous and it has very, very big gaps and it is not complete. Then another very important aspect of this is that there are very special type of cells here which are called Kupffer cells. What are these? Kupffer cells. These are derived from circulating monocytes or macrophages, right? So these are fixed, Kupffer cells are in fact the fixed macrophages, right, present into liver sinusoids, and along with the endothelial cells, Kupffer cells are also lining the sinusoids. So that when blood is moving from the periphery to the center, components of the blood are freely exposed to the Kupffer cells. So Kupffer cells can, blood is also coming from the spleen. If there are fragments of the broken RBCs, they will be removed by the Kupffer cells. Am I clear? So Kupffer cells are present filtering whatever toxins or bacteria or fragments of the RBCs are passing from portal blood, right, or through the sinusoidal blood. Any question up to this? Then, here were your hepatocytes, right? Hepatocytes are large cells. They are about 20 to 30 microns, right? 20 to 30 micron meter. These are polyhedral cells or with multiple faces. You have to remember, one face of the hepatocyte is towards the blood, another face is towards the biliary canalicular system. If you really want to know exactly how hepatocytes are and what is their relationship with the bile drainage system, let me make two hepatocytes here. Now this is their nucleus, right? Usually there is a large nucleus in the center of the hepatocytes, but as your age increases, number of nucleus in the hepatocytes may increase, right? And this was the sinusoidal system. So naturally, this part of this face of the hepatocyte is exposed to the components of plasma. Is that right? This face, which is towards the space of Deci, this has multiple microvilli to increase its surface area, right? Surface area, right? Another thing which is very important, that biliary canaliculi are basically a gap between the cell. They are not, suppose this is one cell membrane going, this is another cell membrane going, and these cell membranes become separate from each other and now they go down. So this is biliary canaliculi. Actually, biliary canaliculi is not lined by any special cells. These are just gaps, grooves present in between the two hepatocytes. It's worth repeating. Biliary drainage system does not start as very special duct. The biliary canaliculi start as a gap or space or the grooves present in between the two hepatocyte membranes. Is that right? And then what is there special? What are the tight junctions here? Is that right? So basically bile is drained from these cells up to this side. And then this tunnel is going in between many cells. Is that right? So here I have shown it in a very wide way, but actually the cells should be touching each other and in between them a very fine tunnel is moving through. Is that right? Am I clear? No problem? Right. Now, these cell membranes are specialized in a different way. For example, the membrane of the cell which is facing to the space of Deci, right? It has different transporter systems and it has different type of secretory system. And the membrane which is facing towards the biliary canaliculi, it has also transporter membranes and proteins, but they are different than the part of the membrane which is facing to the space of Deci. For example, bilirubin, when RBCs break down and hemoglobin break down, one of the breakdown product of the hemoglobin is bilirubin. Bilirubin is from the, a lot of RBCs break down into spleen. From there, bilirubin come into blood, right? And bilirubin is reaching, suppose I make this, bilirubin is coming here. This is a bilirubin molecule. Through the sinusoidal system, bilirubin molecule will come to the space of Deci. Then this surface of the cell has the transporter which will take up the bilirubin to the cell. I am going to tell you how the hepatocyte work, just one example. Then bilirubin will go in, right? When bilirubin is brought here, it is now, after that, this is conjugated with glucuronic acid. Now this glucuronic acid, which is added to the bilirubin, right, by the hepatocyte machinery. Then conjugated bilirubin is actively secreted into where? Biliary canaliculi. You are understanding? So it means that hepatocyte membrane, which is facing to the space of Deci, it should have the transporter to transport the bilirubin from space of Deci to the cell. And once bilirubin gets conjugated with glucuronic acid, then it cannot go back. Most of it will go to the biliary canaliculi, because those transporter protein which can transfer the bilirubin from the hepatocyte to the biliary channel or biliary canaliculi, they are only present in this part of the membrane, right? And there are so many other examples, right? That, for example, from here we can take up many drugs in from the blood, and then drugs are modified, and then in some cases of the drugs, their metabolites are actively secreted into where? Biliary canaliculated system. And in this case, these metabolites will eventually go to GIT and lost into fecal matter. But there are other drugs, those drugs are taken from the space of Deci into this cell, they are conjugated and thrown back to the blood. So they will be lost into urine. You are understanding? The point by these examples I am trying to put in your mind is that different phases of the hepatocytes are specialized in doing different functions. That is why when you will study pharmacology, you will learn the few drugs or their metabolites are lost in fecal matter. The other drugs, their metabolites are lost into urine, because liver is one of the major, you can say, organ which deals with drugs and conjugating the drug or changing the drugs. We call it biotransformation, right? And it depends on the liver cell, the throwing that modified metabolites of the drug into biliary canaliculi or throwing it back to the space of Deci and going to the blood. Am I clear? No problem. Now, this is the exact position of the biliary canalicular system, right? Another thing which is very important, that hepatocyte cells are having lot of mitochondria, 800 to 1000 mitochondria present per cell. They are having lot of lysosomes. They have having lot of peroxisome. You know, they have to destroy all some bacteria which may be wrongly coming from GIT to the portal blood. So hepatocytes should take them, and Kupffer cells should take them and destroy them. Then from the GIT, if the toxic substances are coming, right, they should be catabolized in hepatocytes. So they have a lot of lysosomes, they have a lot of peroxisomes, then they have lot of rough endoplasmic reticulum and smooth endoplasmic reticulum. With smooth endoplasmic reticulum, they are producing the lipids. They are catabolizing the estrogens, progesterone, testosterone, substances like that. And with the rough endoplasmic reticulum, these cells are synthesizing a lot of plasma proteins, right? From this side, they will be taking up the amino acids, then they will synthesize the plasma proteins like albumins, and then they will throw them back to the space of Deci so that they become the part of the blood. Am I clear? So, and another very rather extremely important thing, in the space of Deci here, there is a very special type of cell. This cell is extremely important, especially in pathological conditions. Physiologically, this cell is acting as a fat storing cell or vitamin A storing cell. You know, vitamin A is lipid soluble. Am I right or wrong? Yeah, vitamin A is, of course, vitamin A is lipid soluble, because I say the cell is fat storing and vitamin A storing. Is that right? It stores a lot of vitamin A, right? This cell is called stellate cell, and this is also called ito cells, ito cells. Why I am stressing on this? Because when liver has inflammation for a long time, inflammatory mediators stimulate these ito cells, and they lose their fat and they become very aggressive and dangerous cells. When there is hepatitis for a long time, chronic hepatitis, in the liver, of course, many chemical mediators of inflammation are produced. Those chemical mediators of inflammation can stimulate ito cells, and they convert into myofibroblast, and then they start secreting a lot of collagen. And you imagine that if there is, suppose you have some hepatitis B virus, unfortunately, and that hepatitis B virus is producing chronic hepatitis, then if chronic hepatitis is really for a long time, all the ito cells in your liver will be stimulated, they will start producing a lot of collagen. So your liver will be generalized fibrotic, fibrosis will develop. And of course, these ito cells, when they put a lot of collagen here, this collagen which is produced in this area, because ito cells are here, isn't it? This collagen will constrict around, what is this? Sinusoid. So many capillary system will be fibrosed, or they will be constricted, and liver blood flow will alter. Some areas will have less blood flow and more necrosis. Some area will have over blood flow and hyperplastic nodules will develop. So eventually liver will become fibrotic and nodular. We call it cirrhosis, and these are one of the major player in cirrhosis, ito cell. So how many cells we talk about? Of course, the minimum you should know, liver has a hepatocyte. Is that right? But more important is that, of course, in the sinusoids, there are endothelial cells and there are Kupffer cells, right? But you should not forget that outside the sinusoid, in the space of disease, there is a very nasty group of cells which are called ito cells. Usually they are like good friends, they are not making any trouble, but when they become irritated, they are after your life.
What was the relation to vitamin A?
Usually they are vitamin A storing cell, right? And they store a lot of fat and vitamin A. But actually, when they are irritated by chronic inflammatory system, then they start producing collagen and they start damaging the whole liver architecture. Is that right? No problem. Now, we have to talk about another aspect. I will just draw rapidly that these are your sinusoids, right? And when we are talking about this structure, which I'm explaining here, this is called, what is this? Classic lobule. And in classic lobule, explanation goes like this. In the center there is central vein, and there is a polyhexagonal lobule, and at the corner there are portal triads, right? And blood is coming from the periphery to the center, and the hepatocytes are in between making the, now we'll make it rapidly, right? Hepatocytes are small cells or large cells? They are large cells, and they are having specialized surfaces. One surface is towards the space of disease, which deals with the substances which are coming into blood. Other surface is making, what is that? Billy? Canaliculi. Is that right? And these cells are very rich in lysosomes, they are very rich in peroxisomes, and they have lot of mitochondria, and these cells also have lot of, yes, Golgi operators. That about 50 Golgi operators units are present in per hepatocyte. You know why? Because they are synthesizing lot of proteins. Hepatocytes synthesize, plasma proteins. Albumin, they synthesize the coagulation factors, and they synthesize many other proteins, right? Albumin, alpha globulins, beta globulins, coagulation factors, angiotensinogen, right? And hepatocytes, of course, you should not forget, they also synthesize, yes, what else they synthesize? They synthesize lipoproteins. Do you know about lipoproteins? You know about, especially they synthesize very low density lipoprotein, VLDL, and hepatocytes also synthesize LDL. Hepatocytes synthesize cholesterol also. Do you know that or not? You don't know that, right? So hepatocytes basically produce lipoproteins, especially VLDL. VLDL is secreted by the hepatocytes to the blood, and VLDL act as a carrier of triglycerides, right? Then hepatocytes also synthesize another lipoprotein, which is a bad low density lipoprotein, which is also called LDL, and LDL act as the main carrier of cholesterol. They are releasing, hepatocytes are releasing VLDL, which is carrier of triglyceride, VLDL, very low density lipoproteins. They are carrier of triglyceride, and they also synthesize LDL, which is the main carrier of cholesterol. So hepatocytes can synthesize cholesterol, pack into LDL, and LDL will come here and go to the blood. So LDL will be supplied to the peripheral tissues, and VLDL can also be synthesized by that and secreted in space of Deci, and then they go where? Of course, general circulation eventually, and then triglyceride can be supplied to the peripheral tissues, right? And hepatocytes also synthesize HDL. What is HDL? High density lipoprotein, right? So one of the very important function of the hepatocytes is that they are also involved in synthesis and secretion of lipoproteins. They are also producing. Another very important function of the hepatocyte is activation of vitamin D. Modification, rather I should say modification of vitamin D. Vitamin D comes to the hepatocyte in the form of cholecalciferol. I should write it here. Cholecalciferol. Vitamin D come to the hepatocytes as cholecalciferol, and in the hepatocytes there is an enzyme which is called 25 hydroxylase present, which will do hydroxylation of cholecalciferol at 25th carbon, and then cholecalciferol is called 25 hydroxycholecalciferol. So one of the function of hepatocyte is it converts the cholecalciferol, which is a type of vitamin D, into 25 hydroxycholecalciferol. Then 25 hydroxycholecalciferol goes to your kidney cell. There it get one more hydroxylation, right, at carbon number 1. Then it convert into 125 dihydroxycholecalciferol. One hydroxylation in the liver and one hydroxylation in the kidney. When vitamin D becomes double hydroxylated, then it becomes fully active to deal with the calcium and phosphate. Why it is so relevant? Because in liver diseases and in kidney diseases, vitamin D metabolism may also be disturbed, right? So what we were talking about, these are hepatocyte plates, right? And how many functions of hepatocyte I told you? That they synthesize the plasma proteins, they synthesize the lipoproteins, they also synthesize the, yes, they can secrete the bile towards the, what is this? Biliary canaliculi, right? Can you tell me the components of the bile? I will not go into some simple things that bile as water. I will just tell me the most important components of the bile. Okay, this is a beautiful star. There are 5 things at least you are supposed to know which are present in the bile. Bilirubin, conjugated bilirubin, yes. What else is present? Yes, please. There is also phospholipids and lecithins, which are synthesized by the hepatocyte and secreted into biliary system. And then cholesterol. If you have extra cholesterol in the body, these cells can secrete those cholesterol into biliary system. Then biliary system has, yes please, yeah, this very important thing, IgA antibodies. Let me tell you exactly where they are produced. There are active B cells, the plasma cells here in space of Deci. They produce IgA, and IgA is taken up by the hepatocytes and then pumped into biliary drainage system. So through the bile, lot of IgA come into GIT and protect the GIT against the virus and bacteria and other invading organisms, right? So what else is present in the bile. There is bilirubin, there is phospholecithins, phospholipids, and lecithins, there is cholesterol, and of course, something very important I want you to tell me. There's something very important in the bile. Please tell me bile salt. That's great. Bile acids and bile salts. Bile salts or bile acids, right? Can you tell me some name of the bile acid? Cholic acid and chenodeoxycholic acid. Cholic, CHO, cholic acid, and other bile acid is cheno. I don't know, it's from some Chinese founded. Chenodeoxycholic acid. Is that right? This is the minimum you are supposed to know about bile acids. So these are the components of the bile, right? And of course, you must know there are many drugs which you take, drug for your diseases. Many drugs which you take, many of them are metabolized and their metabolic products are thrown into bile also. So that metabolite should go into urine. Of course, no, sorry, GIT and then fecal matter, yes. Because to throw it back to the urine, the drug metabolite should go to the spacer disc and then into general circulation, then filter through the kidney and go into urine. Now, so we were talking about, so this is which structure? Classic lobule, right? Any question about this classic arrangement? If you have understood this, now I will tell you something interesting. Actually, another way to explain the structure is that, okay, now you open your both eyes and look at the situation, what I'm going to do. You know, what is it? Actually, bile from here is going into that direction. Is that right? Into the periphery. Actually, from adjacent 3 classic lobules, you take 3, what is this? Central veins, and in imagination you connect them. Now you can look at this structure within this triangle as bile secreting structure. As bile secreting structure, and bile is moving to the center. To the periphery. Is that right? And this type of lobule is called portal lobule. In the portal lobule, it is the portal system in the center. In the classic lobule, it is the central vein in the center. Right? Okay, let me make it more clear here. Now these are 3 classic lobule, and when we are looking at a classic lobule, we are basically taking in the center of the liver parenchyma is central vein. So all structure around is classic lobule. Here's the classic lobule, here's the classic lobule. But if you think the central structure is your bile draining system, right? If this is the real central structure, then you have to look at this way. Because from here, bile is coming. Now this triangle is called portal lobule, right? And you know, here liver is acting as exocrine gland. When liver is releasing bile, bile is the secretion, but this is not endocrine secretion. What is this type of secretion? Exocrine. It is not endocrine secretion. Look, endocrine secretions are secreted into blood, and I think everyone knows that bile is not secreted in blood, right? And it is secreted into special ductal system, through which it will be drained away into GIT. So this is exocrine secretion. So when we are looking at liver as exocrine gland, then we can explain the structure of liver as portal lobules. Is that right? But when we look at endocrine function in classic liver is secreting suppose plasma proteins or active vitamin D or 25-hydroxy vitamin D, or it is secreting coagulation factors, right? Or liver is secreting the lipoprotein that because it is secreting its products into blood, and the products or secretions are taken away by the blood. So those are endocrine secretion of the liver. Those are endocrine secretion of the liver. So when we are looking at an endocrine organ, then we are concentrating as classic lobule. When we are looking at liver as a exocrine structure, we are concentrating on a portal lobule. Is that right? No problem. Now let's look at the liver as metabolically active tissue, which is doing special metabolism of glucose, special metabolism of you can say what is this, dealing the oxygen and blood perfusion, right? Now we will look to the lobules of liver as their functional units, right? Now functionally, listen carefully, functionally when you look at the liver, actually the hepatocytes which are on the outer side, they are having better blood supply, and hepatocytes which are towards the central vein, they are having poor oxygen supply. Let's talk about now oxygen supply. I will make one more structure here, diagram. Let's make 3 again. Okay. We will look at these lobules in a functional aspect in reference to oxygen supply, right? These are your central veins, right? Now, if you look at hepatocytes, as you know already that blood is moving from the periphery to the center, right? Throughout, it is moving like that. It means the hepatocytes which are on the outer part, they are having well oxygenated blood, and hepatocytes which are more near to the central, yes, central vein, they are having blood from which most of oxygen has been removed, so they are having less oxygen content, right? I will tell you how we will describe in another way, and that arrangement is called Hepatic Asanas. We have explained classic lobule and portal lobule. In the center of the classic lobule there was central vein. In the center of portal lobule there was portal triad or bile draining system, right? And it takes triangular area from 3 adjacent classic lobule, and the corner of this lobules are at the central veins. Right now we will come to hepatic asanas. Look, the hepatocytes which are present in this area, they are receiving the blood with more oxygen, and hepatocytes which are most near, because as blood is moving in the center, hepatocytes are utilizing the oxygen. So these are getting minimum amount of oxygen. Is that right? So we can say that we can divide hepatocytes into 3 regions from out to inward. This is well oxygenated, moderately oxygenated, poorly oxygenated area. Again here there are well oxygenated hepatocytes which are in this area, then there are moderately oxygenated and poorly oxygenated, right? So actually because the hepatic artery and vein, they are present over here, but they are running septal branches from where multiple branches are going in. Now this area which is the, okay, I will draw like this, hepatocytes which are present in this area, here, in this area, here, these are well, they are receiving the blood first of all, and these hepatocytes are having maximum amount of oxygen. Now it has some, and these are the hepatocytes which are exposed to minimum amount of oxygen. This is called zone 1, and this innermost is called zone 3, and this is the zone 2. So what we do, that according to the oxygen content of the blood as it is passing through the sinusoids, we can classify the structure of the parenchyma. This type of arrangement, right, like this, and this become a diamond shape. This is called hepatic asanas. This is called hepatic asanas, and this is its long axis of hepatic asanas, and this is its short axis. In the long axis, as you move from the periphery to the center, first there is zone number 1, then zone number 2, then zone number 3. Is that right? And in the short axis, there are in the septa, connective tissue, portal vein branches and hepatic artery branches are running, and they are feeding the hepatocytes. Now, if we come to this structure, let's suppose we come to this structure and find this lobule. Actually, in this way, in this classic lobule, what we'll do, that will connect the two central veins. This is the long axis, and from this striate here, this is the strength. Now, in this structure, this will be your zone number 1, this will be your zone number 2, and this will be your zone number 3, and same is on opposite side. Well perfused, well oxygenated blood, moderately oxygenated blood, and least oxygenated blood. Now you may be thinking why Dr. Najeeb is obsessed with this idea and he has repeated so many times. There is a lot of applications of this concept. For example, if there is severe ischemia to the liver, if there is severe ischemia to the liver, oxygen supply to the liver become very less. In which zone cells will die first of all? Zone number 3. Is that right? Zone number 3. Is that right? In congestive cardiac failure, heart is pumping poorly and many organs in the blood are receiving less oxygen, and liver is also receiving less oxygen. So in congestive cardiac failure, what really happens, that in which zone hepatocytes will undergo necrosis and ischemia? Zone number 3. Now zone number 3 is around near the, what is this? Central vein. Actually, for this lobule here, then there is another lobule on this side, again here, here, and here. So what really happens, zone number 3 hepatocytes are basically pericentral hepatocytes. Pericentral hepatocytes. Now, if someone has congestive cardiac failure, then what really happens, these are the hepatocytes which will undergo severe ischemic injury. Is that right? Because they are comprising in the zone number 3. Is that right? So what they will happen, that either they will go into full necrosis or they will become loaded with the fat, because the lipid which they are receiving, they cannot catabolize, and whatever they are synthesizing, they cannot secrete. So they become loaded with the lipid. So we say that in case of congestive cardiac failure, there is pericentral necrosis of the hepatocytes. Or someone develop severe circulatory shock. He loses severe hemorrhage and blood has gone out. Of course, blood to many organs will be reduced, including the liver. If person survives and you take later on biopsy of the liver, which cells in the liver will be necrotic? Pericentral. Or zone number 3, zone of hepatic asanas. Am I clear? This is one clinical application of this concept. Another clinical application is, okay, I will start, first I will explain in detail zone number 1, then 2, and then 3. Zone number 1 is the area in which hepatocytes receive maximum amount of the nutrients from GIT. If you have eaten the food, a lot of glucose is coming from the GIT. Of course, zone number 1 hepatocytes will receive the glucose more, and from the pancreas they will receive the insulin more. So they will be metabolically differently active as compared to the hepatocytes which are present in zone number 3. Am I clear? For example, if glucose is coming in moderate amount, maybe most of glucose more glucose will be taken by the hepatocytes in zone number 1 and less glucose will be taken up by the hepatocytes in zone number 3. So in zone number 1, hepatocytes are exposed to larger concentrations of nutrients and of course oxygen. Plus, if there is chronic hepatitis, now this is very important, if there is chronic inflammation in the liver, during inflammation what happens? Inflammatory cells will come into liver and parenchyma. A lot of neutrophils and macrophages will spill into liver parenchyma. Is that right? Which zone will suffer first? 1. Because look, these are the hepatic arteries and this is the blood coming, and from this area white blood cells will start coming out. So actually this is a very classical picture. When there is chronic inflammation of the liver, the hepatocytes which are outer in zone number 1, they are exposed more to the incoming neutrophils and macrophages than the hepatocytes which are in the zone number 3. Am I clear? This is another way that how this zonation concept is important for us. Then there are some toxins which destroy the hepatocytes. For example, someone tried to commit suicide by taking a lot of organophosphates. You know, they used to kill the rats and mouse like that. So, if in your toxins or poisons, if someone has taken a poison with a lot of phosphorus or with a lot of manganese, right? Or sometimes there are some bacteria like Proteus vulgaris, they produce toxins. If these toxins are coming into blood, do you think zone number 1 will be first exposed or 2 will be first exposed or 3? So 1 will be suffering most, toxic injury. So in many inflammatory diseases will damage zone number 1 more, many toxic poisons will damage the zone number 1 more, nutrients and hormones which are coming from pancreas, they are working on the zone number 1 more, right? Then I will talk about zone number 3, and zone number 2 has characteristics which are intermediate to zone number 1 and 3. In zone number 3, already we have mentioned that this is the zone in which necrosis, ischemic necrosis will do the maximum damage. Ischemia to the liver will do the maximum damage in the zone number 3. Then another thing, that in the zone number 3, there are some toxic substances. Listen now carefully. There are some other toxic substances, they are taken up by the hepatocytes, and to detoxify those substances, hepatocytes need a lot of oxygen. For example, there is carbon tetrachloride, this is a toxin, right? Or there is tannic acid, or there is chloroform. Now, to detoxify these toxins, hepatocyte need a lot of oxygen. If someone is exposed to such toxins, right, then damage will be more to the zone number 1 hepatocytes or zone number 3? Zone number 3, because they have minimum oxygen, and to toxify such substances, actually toxin will be of course passing from zone number 1 to 2 to 3. Even the toxin is coming first to the zone number 1, but zone number 1 has enough oxygen to detoxify those compounds. But zone number, because here the compounds detoxification is dependent on oxygen availability.
So anything oxygen dependent would reflect in zone 3.
Yeah, so the whole purpose of this talk is that I am trying to tell that functionally, if you want to look at the parenchyma of liver, then you should look with the concept of hepatic asanas. Hepatic asanas is, you can say, diamond shaped structure extending from one central vein to the next central vein, and the long axes are in between the two central vein, and short axis is extending from one portal triad to the next portal triad. And the point which you have to remember, that the hepatocytes which are more near to the portal triad, they are having more oxygen, and hepatocytes which are most near to the central vein have minimum amount of oxygen, and due to that reason they may have different functional activities and functional and different pathological factors affecting them. Right, so after that what else we should talk about? Okay, let's sum up the function of the liver, right? What is the function of liver? Yes, please. Who will tell me the function of liver one by one? Of course, first of all, it is having exocrine function. Exocrine function is that liver is a gland, isn't it? So it has exocrine function. In exocrine function, what it is doing? It is making bile, and we have discussed all the components of bile. Is that right? That is this exocrine function. Then liver has endocrine function. It secretes lot of substances in blood. There we have already talked the plasma proteins like albumins or alpha globulins, beta globulins, then fibrinogen, prothrombin, and other coagulation factors, right? Or lipoproteins, right? Even we did not mention that in deamination of the, what is that? Amino acids, right? Ammonia is produced and then urea is produced. That is also a function of hepatocytes, and it secretes urea into blood, which will eventually pass out through urine. Is that right? Then it was having metabolic functions like converting the glucose into glycogen when the glucose level in the blood is high and insulin level is high. But what really happens when in between the food, when blood glucose level goes down, then hepatocytes or liver has another function that it will break down the glycogen into glucose. So one of the function of the liver is that it is stabilizing the blood glucose level, right? That when there's high glucose level, it will convert the glucose into glycogen. When blood glucose level is down, it will break down the glycogen back to glucose and release the glucose into blood. Then it has one more very interesting function, gluconeogenesis, right? That if there is blood glucose level is really down, then under the directions of glucagon and other hormones, it can synthesize glucose from non-carbohydrate sources like from the amino acid breakdown or from the fatty acids, right? Breakdown, it can eventually produce glucose, right? Then it has a very important function of detoxification. As we discussed, many toxins coming from GIT are taken up by the hepatocytes and they are detoxified, and in another way that many drugs which you take, they are also metabolized in the hepatocytes and they are altered. We call it drugs biotransformation. Many hormones in your body are also catabolized by the hepatocytes. Then of course one more function was hepatocytes could take up the IgA from the space of DC plasma cells and pump them into biliary canalicular system. Eventually they will drain into GIT. Is that right? Any question up to this? Just to sum up, the bile drainage system. Bile drainage start from this center. Here there was bile canaliculi. As they move more on the periphery, they become wider and they may be lined by special cells. Then they are called canal of Hering, H-E-R-I-N-G. Okay. So bile canaliculi convert into canal of Herings. Then they come here and they convert into colongules, and colongules come together and make, what was this? Bile ductules, and then bile ducts. Then bile ducts fuse together and make left and right and the left bile duct, then common bile duct, then we lost. Go back all the way. Look, in between the hepatocytes, what was there?
Left and right.
You will tell me. No. Start from the hepatocytes. Bile canaliculi, then canals of Hering, then colongules, then bile ductules. Bile ductules or bile duct beginning at the bile ductule which are present at the portal triads or portal areas. Then bile ductule go into, all of them fuse, some of them into right bile duct and then left bile duct. Then right and left bile duct become together and become
Common bile duct.
common hepatic duct, because right hepatic duct and the left hepatic duct. I think my glucose level is down also, right? Common hepatic duct. Then cystic duct will come and then it will become common bile duct, right? And eventually with the pancreatic duct, common bile duct fuse together and they drain at the ampulla of Buerter in the second part of duodenum and release the bile and pancreatic juices there. Is that right? Any question about all this thing? Okay, I'm going to take a test before I leave you, right? First of all, classic lobule, it has which structure in the center? Central vein. Portal lobule has which structure in the center? Portal triad or bile duct system, right? When we talk about hepatic asanas, then zonation of hepatocytes are done according to the level of oxygen supplied. Is that right? Then there is another question. How many, in the liver, how many input system are there? Portal vein, Then there is hepatic artery. There are two input systems. How many output systems are from the liver? There are again two. One is the hepatic vein out and other is the lymphatic system out. You forget that. Is that right? Then liver is, all parenchyma of the liver is covered by a very strong capsule that is called capsule of Gleason, which is of course made of lot of connective tissue, and from that capsule septa go inside the liver. They divide the liver into lobes and then lobules, and those are the lobules we were studying, right? Another thing. The blood is moving in a classic lobule from the periphery to the center, and bile is moving in the classic lobule from center to the periphery, and lymph is moving in a classic lobule from center to the periphery. Is that right? Few clinical points. Of course, you will study in pathology in detail that liver is a very favorite from some virus. Hepatitis A virus attacked the liver, and hepatitis A virus is acquired by orophycal route, and it is also called infectious hepatitis. And hepatitis A virus produces acute hepatitis, but usually does not produce chronic hepatitis. Then there is another virus, hepatitis B virus, which is transferred by blood transfusions or body secretions, right? And hepatitis B virus produces acute hepatitis. It may also produce in some people chronic hepatitis, and if chronic hepatitis is really prolonged, then patient may have cirrhosis, and sometimes even in such liver, what may develop? Hepatocellular carcinoma may develop. Is that right? Then there is hepatitis C virus. That is also coming through blood transfusions, or it is coming through the body secretions, and hepatitis C virus produces lot of chronic cases of hepatitis, and in patients who are suffering with the chronic hepatitis due to hepatitis C virus, they also have a high risk to develop cancer in the liver. Is that right? Then we can talk about, yes, we can talk about jaundice. For jaundice, we have 4 videos in the pathology, but here I will just tell you one thing. In jaundice, there is a high level of bilirubin in your blood. Why bilirubin level should be high in the blood? One reason may be RBCs are breaking down excessively, and a lot of bilirubin is produced and liver cannot handle that. Other mechanism of jaundice may be that hepatocytes are unable to take up the bilirubin from the blood. Another mechanism may be that bilirubin is taken up by the hepatocyte, but within the hepatocyte, enzymes which are supposed to conjugate the bilirubin with glucuronic acid, those enzymes are called glucuronide transferases, those may be deficient, right? Then bilirubin cannot be handled. Another mechanism may be that hepatocyte take up the bilirubin, conjugate the bilirubin, but they cannot secrete the bilirubin into biliary canaliculi. Again, bilirubin will go back to the blood and jaundice. Let me make a simple diagram. Let's talk from here. This is your spleen. Either there is too much, number one mechanism is too much RBC breakdown, and so much bilirubin coming that hepatocytes cannot handle. Number two mechanism, that bilirubin is coming in normal, but hepatocytes are unable to take it. Number three mechanism, within the hepatocyte, hepatocytes are unable to conjugate it. Number four is they conjugate it well, but they cannot secrete it to the biliary system. This was fourth. Fifth is that biliary system drainage within the liver is impaired. We call it intrahepatic cholestasis. Cholestasis means stasis of bile. Bile cannot drain. Or through the liver, bile come out, but common bile duct or other part of the main ducts are blocked. We call it extrahepatic cholestasis, or simply we call it extrahepatic bile flow obstruction. That is the sixth mechanism. So mechanism number one for the jaundice is too much breakdown of RBCs and bringing too much unconjugated bilirubin there. Number two is that hepatocytes are unable to take up the bilirubin. Next mechanism is hepatocytes do take up, but they are unable to conjugate. Next is they do take up and conjugate, but they are unable to secrete into biliary canalicular system. Then next is biliary canalicular system is blocked within the liver, and next mechanism is bile drainage system is blocked outside the liver. Is that right? So all these conditions can produce jaundice, right? Important thing, if RBCs are producing more bilirubin, or bilirubin is not taken up, or bilirubin is not conjugated. All these conditions will produce unconjugated hyperbilirubinemia, because bilirubin is not getting conjugated. If there is too much bilirubin production, or bilirubin uptake by hepatocyte is impaired, or bilirubin conjugation is impaired, and first three mechanisms, what will happen? What type of bilirubin in the blood will be high? Unconjugated. Then onward, if bilirubin is getting conjugated, but after that, if it cannot be secreted into biliary canaliculus, or it cannot drain down, it means bilirubin is getting conjugated, but it cannot go to GIT, so spill back to the blood, that is conjugated hyperbilirubinemia. Right, we will discuss in detail these things when you will study patho. Is there any question? No question? Class dismiss. Thank you.